Here. Okay, so this is just a brief overview of Chapter 9 here. Periodic table, Mendeleev. Here we can see the periodic law, just how things vary in a periodic manner. This is going across the, like, lithium, right, to sodium, sodium to potassium, potassium to rubidium. So we can see the periodic law. But what is this? This is atomic volume. So we can see how the volume increases. Yeah, but we aren't going to worry about the atomic volume right now. And so you don't have to worry about that table. This is just an old version of the periodic table. There's some missing elements. And so those missing elements were predicted to exist and they were discovered, right? Do you know one of the missing ones? Germanium. Germanium was predicted to exist, but they didn't find it until 1886. It was predicted in 1871. Just because there's a hole missing there. This is the X-ray emission spectra of different substances. So X-rays, what do X-rays do to matter? Ionize. And so typically what we're looking at is we're looking at knocking a core electron out. X-ray emission is you knock a core electron out and eventually a valence electron drops back down to fill that missing core because it's totally unstable. And so when a valence electron drops back down to the core, it emits X-rays. And those X-rays are characteristic because, the drop down is not the same for every element. They're allowed energy levels. And so this acts as a fingerprint for different elements. For example, when they on the lunar lander, they had this X-ray photoelectron emission spectrometer. It's called XPS. And then they can blast the rocks with this and measure the spectra of the rocks and determine what elements are present in the rocks, based on their fingerprint. So copper has these lines here corresponding to specific transitions. Nickel is different, cobalt's different, iron's different, manganese. And so this is great for what we call elemental analysis. In fact, this is one of the techniques that's often used to analyze, alloys, mixtures, whatever else. One of the classic mixtures here is brass. Brass contains copper. Do you see the two lines of copper here? It also contains, what else? Other stuff, which is not here, but there's other stuff there. But definitely you can see there's copper and brass. And then these lines would correspond to some other element, whatever that is, zinc. And so here is the here's how it works. You can read about it. Which version of the periodic table is this? This is kind of weird because at the beginning of the book, Petrucci has the other periodic table. On the exam, you're going to have this periodic table. For this periodic table, what is uranium? Is it 5D3? I mean 5F3 or 5F4? 5F3. You see how it splits here rather than splits here? And so just be aware of that. But anyway, you guys already know this, right? Yes? You guys know that you should know the alkali metals, the alkaline earths, the transition metals, the lanthanides, actinides. Right? These are lanthanides, these are the actinides. Main group are these two. The halogens, you know those? The noble gases. These are called the chalcogens. These are called the pnictogens. This is the carbon family. Alternatively, you could call this the carbon family, the nitrogen family, the oxygen family, the fluorine family. If you don't want to memorize those names. Metals. What are metals? What's the definition of a metal? Do you know the definition of a metal? A metal Yeah, a metal is a substance that is a good conductor of heat and electricity, right? They're malleable and ductile. They have moderate to high melting points. They also tend to lose electrons when undergoing chemical reactions. Lose electrons. So metals have a pretty good definition, but nonmetals don't. The definition of a nonmetal is all screwed up because there are so many different kinds of nonmetals. Are all nonmetals non-conductors of heat and electricity?
No.
No. For example, diamond is a great conductor of heat. Graphite is a good anisotropic conductor of electricity. And so nonmetals don't really fit so nice. Are they all brittle solids? Well, is chlorine a brittle solid? No. Some are gases at room temperature. Well, that's true. And so the definition of a nonmetal is not so good. The definition of a metal is good. But a lot of people say, well, what is a nonmetal? A nonmetal is not a metal, and it occurs on the right side of the periodic table. Right? Nonmetals tend to gain electrons. They have much more widely varying properties. Metalloids are the elements that resemble both. They're at the transition zone. And metalloids are at this at the stair step here, right? Do you guys know the boundary? And so the elements touching this have properties of both, a metal and a non-metal.
What is AT?
AT? This one? This is iodine. This is atrion. I don't remember. That's a good question. But AT, you know, AT, the problem with AT is you're not going to see that very often. Do you know why? It's radioactive. And AT is going to have a very, very short half-life. Half-life means it doesn't live for very long. In fact, I know this one. I think this is actinium. Actinium. This is polonium. I know this one for sure. Polonium. Have you heard of polonium before? You haven't heard of polonium? If you want to see the devastation of, actually, should I waste more time? Have you heard of the polonium tea?
No.
This guy. This is what happens when you have polonium tea. This is like the secret espionage thing. Have you heard? This is some famous Russian guy. I forgot what, but apparently some KGB agents or something spiked his tea with polonium, and he had a miserable death, unfortunately, because polonium is a radioactive substance which emits alpha particles. And yeah, it's pretty sad. And he's not the only one. Two female journalists from Russia also polonium poisoning in Los Angeles. Yeah. Thank you.
So where do you find it?
Wait, how do you have access to I got some polonium.
Talk once and many words.
Wow, Swiss scientists, I didn't even know this. Yeah, this is the very famous case, you know. It was used to kill KGB agent turned Kremlin critic Alexander Litvinenko in London, 2006. And that's that guy in the pictures. Do you guys remember that? Yeah, he's poisoned. I guess Yasser Arafat might have been poisoned by polonium here. Too. What is polonium?
Is it like a liquid?
Yeah. If ingested in small doses, a minuscule amount of silver powder solid is sufficient to kill. British radiation experts say once polonium 210 enters the bloodstream, its deadly effects are nearly impossible to stop. How can it poison people? This is NBC News. So people can be poisoned if they eat or drink food contaminated with it. And so this is, Litvenko drank tea and they found traces of polonium all over, I think, the glass and other things. Symptoms of polonium. Where does it come from? Here it is. Actually, I don't know where polonium comes from, but we can find out. Byproduct of chemical processing of uranium. But usually it's made artificially in a nuclear reactor or particle accelerator. British radiation, John Croft said a dose large enough to kill would likely have to come from a government with either civilian or military nuclear capabilities. Oh, can the radiation be detected? Yeah, polonium's large alpha particles of radiation do not penetrate the skin and don't set off radiation detectors. Most radiation detectors only detect ionizing radiation because that's how the Geiger counters typically work. You have to ionize a gas inside the detector that causes an electric current, which sets off a signal. To have alpha particle, you know, when you buy a radiation detector, you know, most of them are for gamma radiation only, most of them. And so they only detect gamma. But if you want one, and there are radiation detectors that detect alpha, you can buy those. Or you buy a test kit, like radon, you know, the radon test kit at the home. They have a substance in there. And so you set it out in your house for a certain amount of time, and then you seal it up in the mail, and then ship it out. And then they analyze it for how much radon you have in your house. It's not a real-time thing. You send it out. But they don't set off the radiation, so it's relatively easy to smuggle across international borders. So this is why they're talking about like dirty bombs and that type of stuff, you know, using alpha emitters. All right. So you could read more about it. Let's go back to this. How about bismuth? Do you think bismuth is radioactive?
Yes.
No.
No?
Take a look. You know how I can tell? Look at the average atomic mass. When you look at the average atomic mass, do you see these ones in the parentheses?
That's what it says.
Too hard. Too hard. These are radioactive. How are you going to put it on the balance to weigh it or do things like that? You know? Or put it in the mass spectrometer. You put it in the mass spectrometer, by the time it hits the detector, it's already decayed. A lot of it's decayed. Right? And so they have, you know, to get it precise, that's 209 roughly, 210 roughly, 222 roughly. But you see lead is okay, bismuth is okay. And so it starts going radioactive at about element 84. And we see. Sorry.
So why are not all of them here?
Why are not all of them here?
Like after
Okay, these transuranium are man-made. For example, californium. I know this one. Berkelium, curium, americium, and plutonium. These are all man-made. And so they've been successful at making, actually somebody I think has made 110 and a few of these others. So this table's old. But it's just because nobody's made them yet and detected them. But people are trying to make these. And so these ones here are blank because there's controversy about the name and who gets to name it, right? And so this blank hasn't been discovered, this has been discovered, this has been discovered, and this has been discovered.
how can you make it?
How can you make an element?
Yeah, matter can do this, create out of this.
How they make elements is like what they were talking about, linear accelerator. They accelerate two atoms with huge amounts of energy. You know, an atom, a huge amount of energy is not so huge, right? And so you accelerate these, and then you get the atoms to crash into each other and fuse, like the sun. Do you know the sun is making helium? How does it make helium? It fuses two hydrogen isotopes together, tritium and deuterium. And so that's how they made these. They don't last very long, though. Okay, here we go. All right, metals tend to lose electrons. Non-metals tend to gain electrons, and then we have this border. Semi-metals can do what? Go both ways, either lose or gain. Because we talked about the charge. We expect copper plus to be, you know, this is pseudo-noble gas. Do you know why they call this pseudo-noble gas? It's not really a noble gas, but it does have a filled, it has a filled, like copper plus has a filled D subshell. That filled D subshell is why they call it pseudo-noble gas. It's pseudo-noble gas because it's got that filled. It's not a full filled shell, but it's a filled D subshell, which means it's fairly stable, and it's hard to break apart a D subshell. And so this is why they call it pseudo-noble gas. We also talked about silver, right?
Yes.
Silver, the only charge for that's +1. Zinc, +2. Cadmium, +2. Gold should be +1 like silver. It's in the same family, but gold 3 is also common. And yeah, gold 3. Copper 2 is very common. And gold 3 and copper 2, they're stable for another reason. We have some of these elements here. This follows the 18+2 rule. In the configuration labeled 18+2, all outer shell electrons except the 2s electrons are lost, producing an ion with 18 electrons in the next to outermost shell and 2 electrons in the outermost shell. So for example here, in tin 2, what happens is, normally tin has a 5s2, 5p2. And so in the 18+2 rule, what happens is the 5p2 electrons are lost, leaving us the 5s2. The 5s2 would be a filled subshell. The 5p2 would be a partially filled subshell. And so we have the 18+2 for like tin 2, lead 2. The common charges of tin 2 are +2 and +4. And so the +4 charge comes when we lose the remaining 2 valence electrons. Is that clear? Or do you want me to write it down? Could I write it down? Okay. Write it down. All right, let's take tin, for example, here, since the electron configuration is written. Tin has normal electron configuration of argon, 3d10, 4s2, 4p6, 4d10, 5s2. Okay, there are 2 ways to write the electron configuration. This is not the normal way. The normal way of writing the electron configuration is like this. Remember the 1s, the 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s. So we're going up to the 5s. And so we go to argon. Argon fills the 3p. And so we're left with 4s should go next. And so normally when we write tin, it's argon, 4s2. After the 4s comes the 3d, right? 4s to 3d, that's 3d10. And then after the 3d comes the 4p. This is 4p6. And then finally, the 5s2. And then, actually, 5p2.
So what are they doing?
So why are they doing this? It's because this is written in the order that the orbitals fill, right? This is written in increasing n. Remember, the way the orbitals fill is via this chart, but the way the orbitals are vacated is by n. And so if we're looking at filling, this chart is very useful. I mean, this electron configuration on the top is very useful because we fill them in this order, right? But if we're looking at in terms of ionizing, which electrons are lost first? The highest n. And so this one here is more useful for looking at which electrons are going to be removed from the atom first. And so we have two that are common, and the two ways of expressing is in order of filling or in order of n. Everybody see that? And so when we're looking at ionizing, it doesn't really matter here, but let's say if we're going to ionize a d electron or an s electron, the 4s or the 3d, which one would be lost first? The 4s. And so do you see we're going to have to go around this, but we aren't really going around because the 3d is much closer to the nucleus. Whereas here, it's already in order. We're going to ionize the before the, do you see? And so this is why the two methods are common. So now we're looking at removing electrons. And so if we have tin has the valence. This is the valence here. 5s2, 4p2. Actually, I forgot I should keep going here. There's a 4d10. And so I'm sorry, I need to insert that here. It goes 4s2, and I mean 5s2, 4d10 to 5p2. And so this comes to the 18 plus 2 electron rule. In other words, all we're doing is this. Okay, when we ionize, either diagram shows it correct. When we ionize the first 2 electrons. When we ionize the first 2 electrons, which one are we going to ionize? The 5p. And so let's ionize those. Let's ionize those. So we just got rid of the 5p, right? Now we're at tin plus 2. But tin plus 4 is also a common charge. And so what should we do? Should we ionize 2 of the 10 d electrons here? Or should we ionize the s before the d? The s before the d. Why? Because it has a higher n value. And so in this diagram, we have to jump around the 4d and ionize the 5s. Whereas in this diagram, well, it's nice and in order, so we'll just take those out and ionize those. But we end up with the same electron configuration. So this would be tin plus 4. Tin plus 4 obeys the 18 electron rule. Remember we filled that shell at 18 electrons? And so now we're at a filled shell configuration. Tin plus 2 obeys the 18 plus 2 rule because of those 5s being ionized in sequence. Okay? All right. Turn that on. Okay, let's continue. These ions don't follow any particular rule. You know, if you want to do the 18 electron rule, then iron would have to lose a whole bunch of electrons. No. A whole bunch. And so these ones, there's a balance between losing electrons and forming stable bonds. Okay, nonmetals gain electrons. Know that. Sizes of atoms. The sizes of atoms, you know, atoms, if you were to take a probe and probe the surface of a sodium atom, would you hit a wall, a solid boundary? No, it's just an electron cloud. And so it depends on how forceful your probe probes in. You know, you could, you know, technically you could probe it all the way to the nucleus because there's no wall. And so how we measure the size of the atom is kind of tricky. You know, one way we could measure the size of the atom is based on the 95% boundary of the outermost orbital. Right? But that's not very convenient. The best way of measuring the size of the atom is to bond it to something. If we bond it to something, then, you know, but it depends on how strong the bond is. If the bond is very strong, what tends to happen is it pulls the atoms in closer, making the size appear smaller. If the bond is weaker, then it doesn't pull it in. And so the size of an atom varies depending on how strong the bond is. Therefore, we're going to group bonds into different categories. For example, this would be a covalent bond here, or the covalent radius. And so two sodium atoms bonded together to form an Na2 gas molecule. It's not that stable, but it can exist. And then you measure it. You measure the distance between the nuclei. Now, can the distance between the nuclei be pinpointed both precisely and accurately? I mean, can you pinpoint the position of an electron? Yes or no? No. Because of the, what principle? Heisenberg's uncertainty principle. Does the Heisenberg uncertainty principle apply to the nucleus? That is, you know, are we going to have trouble pinpointing the nucleus, or are we just going to get a probability of where that nucleus exists? Well, the nucleus can be pinpointed with a high degree of accuracy because it is much more massive than an electron. You know, have you ever thought about pinpointing an electron? How do you observe, or how do you detect an electron? Can you see it with your eyes? No. And so how do you do it? You know, well, that's actually not so easy. If you're to pinpoint a bird, you just look at it. It's right there, right? But let's say you're blind and you're trying to pinpoint a bird. What would you do? If you're trying to pinpoint the position of the bird, if you're blind, you might throw little pebbles at it until you hear a squeal, right? And then, oh, the bird must be over there or over here, right? But think about it. It's the same thing. How can you pinpoint the electron? We can't see it. And so what do? You throw little pebbles at it. You know what those pebbles are? Those pebbles are photons of light. But the problem is they aren't pebbles. When you're looking at an electron, okay, you're throwing big rocks at it. That would be kind of the analogy. And so what happens is, let's say you're trying to measure the position. You have a bowling, maybe not a bowling ball, but let's say, whatever. You have something that's very light, and then you're shooting something at it. Are you going to measure its position very accurately? If you're shooting something at this, it's going to move each time you hit it, right? And so originally it was here, but when it moves and it bounces off, then you've just changed its position. And so this is the problem with pinpointing electrons, because anything you use to pinpoint an electron is going to interfere with the position of that electron or the momentum of that electron. And thus we have the Heisenberg uncertainty principle. But if you were to hit the nucleus with a photon of light, do you think the photon is going to perturb the position of the no, the nucleus is massive. And therefore the nucleus isn't going to suffer from the same type of uncertainty that an electron would. And so pinpointing this is easy within the precision of our measuring devices. So we can get a lot of sig figs here, and you know.
Just so you could pinpoint the nucleus?
Yes, you can pinpoint the nucleus. You can't pinpoint the electron without screwing up its position or without screwing up its energy. So the sodium atom's radius is going to vary. For example, this is in a diatomic molecule of sodium. But if we put it in sodium metal is going to have a whole bunch of sodium atoms packed together in a lattice. You see the radius changes because there are going to be other sodium atoms pulling this one away, this way, and so the radius does change. And so it's just this interaction. It's these very soft balls, and where they meet, depends on a number of factors. Here we see the sodium ion. And the sodium ion is definitely going to be a lot smaller because it's missing a electron. When it misses, it's just missing one electron, so should it just be slightly smaller? Sodium has 11 electrons, and so if it loses one electron, shouldn't it be about 1/10 smaller? No. It turns out if it loses one electron, what happened to the size? It got cut in half. And so typically when we're looking at, when we form cations, the cations shrink by half. When we form anions, anions have just one extra electron, but the size doubles. And so there's a profound effect in size from gaining and losing an electron. And I'm going to stop this and finish this chapter. I guess we're going to have to finish this on Monday. When we're thinking about these periodic tables and size and all these other things, we have to look at the interaction between the nucleus and the electrons surrounding it. And so if something loses one electron, like sodium, if sodium originally had 11 electrons, it loses one, now it has 10 electrons. It still has 11 protons. And so the 11 protons acts like a tractor beam and pulls in all the remaining electrons much closer. It doesn't have as much work to do. And so we're always looking at the interaction between the positive charge in the nucleus and the electrons surrounding it. And that charge is called Z. And so if we have 12 protons here, this would be magnesium. We've got 12 protons here, then we look, okay, these are the 1s electrons. Oh, actually, no, this isn't. These are the outermost electrons. These are the valence electrons. Do you see this gray area here? What they're saying here is this. There are 10 electrons in the core. These are the core electrons. The core electrons form a spherical shell of electrons. And this says screen of electron charge from 10 core electrons. And so if we have 10 core electrons in here and 2 valence electrons out here, if I'm a valence electron here, will I see the full plus 12 charge of the nucleus? No, it's shielded. The 10 core electrons, since they're inner shell electrons, effectively shield it perfectly. And so if we have 10 electrons in the core and 12 positive, then Z effective, that is the nuclear charge this electron sees, is plus 10, not plus 12. And so in other words, plus 12 minus 10 gives me plus 2. That's my Z effective. That's a crude calculation or crude approximation. And so what we're interested in Z effective, the higher the Z effective on the outermost electron, the smaller it is. And so if Z effective is plus 2, it pulls it here. If it's plus 3, it pulls it in closer. Z effective plus 4 pulls it in even closer. Z effective plus 0.5, it can get further away.
So the higher it is,
the higher the Z effective, the stronger the pull on the electron, and the smaller the atom. And so we look at the lithium has 3 protons, right? Beryllium has 4 protons. Boron, 5 protons. And so we could see as the number of protons increases, the size becomes smaller. Fluorine has 9 protons. Neon should be in here, but it's not. Then we jump to sodium. Sodium has 11 protons. So take a look at what happened to the size. We went from 9 protons in fluorine to 11 protons in sodium, but the size jumped up. And so we got to figure out why that is, because as the number of protons increases, the size should decrease because Z effective should be increasing. But we'll take a look at that
Isn't that because it's on the
Because it's another shell.
Yes, it's in the next shell. That's exactly the reason. Maybe I'll just say it here. When we add a proton, we also add an electron. And so let's take a look at the periodic table. When we add a proton, we also add an electron. But why doesn't that electron cancel out the positive charge? And so here we went from +3 to +4, but we also added one more electron. So shouldn't that electron cancel out the additional positive charge? The reason it doesn't cancel out is it's because it's a same shell electron. Is the same shell electron effective at shielding? No. Same shell electrons are poor shielders because they're in the same shell. And so sometimes they block, sometimes they don't. Whereas inner shell electrons are very effective shielders. They're going to shield 100%. And so let's take a look at what happens when we go from lithium to sodium. When we go from lithium to sodium, do you know, actually, what happens here? Let's go from neon to sodium. When we go from neon to sodium, we go here. We go and we put that electron in the next higher energy shell.
It's a little bit bigger.
And so that means all the other electrons are going to be fully shielded. And so it has to do with same shell versus inner shell shielding, and this is what accounts for that jump in the size. And we're going to look at this in more detail. I'll write it on the board, but I'm going to stop here. We didn't get very far in this chapter, but there's not much because in this chapter we have the size, and then we have the
Electronegativity.
ionization energy, which is related to the exact same thing as size, electron affinity, which is related to the size, and other stuff. So what we're going to do right now is we're going to go into the computer lab.